chow. Yeah, that's the abbreviation for gun chow.
All right, so as we move on, now we talked about what entropy is. We did not ever talk about how to measure entropy. You know, we talked about how to measure delta H. There were a few different ways. You could use the bond energy or the thermodynamic table or use calorimetry. With entropy, we use the thermodynamic table for that too. Remember, if you remember looking at that, the table in the appendix of the book, there's the three columns. One was the delta H, heat of formation. One was actually the delta G of formation. And then one was the entropy value. So we would use the entropy values to find delta S for a reaction. You'll be there in the appendix of the book as you do the homework assignment. Just take the products minus reactions. Now what's really nice is that the entropy values are all positive, unlike the delta H, which almost all of them are negative. So it'll be easier to calculate delta S. Yes?
So for the second equation, is that only for surroundings? Like,
yes, it's only for surroundings. Yeah. So yeah, this is how we find the delta S of the system. This is how we find the delta S of the surroundings. Today it's all about measuring entropy and delta G. Delta G is a biggie.
You have a lab?
No lab. No. So the quiz is going to have 4 chapter 17 questions and then a review quiz.
So no lab?
That's what he said.
What did you just say?
Labs are like military.
Labs are great killers.
Labs are, no, not.
I tell people that I do bad on labs and they tell me I'm an idiot. Yeah, that's what Kyle said. Yeah, that's what Kyle told me too. But he said you're on test and then... why are you in the house? Come on, man. You're doing something educated. Get on that.
Where are you running yours?
In the weight room?
Where are you running?
Weight room, bro.
Treadmill.
They're pretty nice.
Yeah, they're good. I just
I
like
see my
what size.
Friday then.
We'll see you Monday.
Oh, it's swim team? Good.
You don't go to the gym, are you?
I'll see you. Yes, Jeff.
What's the most you can bench?
I haven't benched and lifted in a long time. I was in the 200s for a while, but I wouldn't be able to now. I was in the 200s for a while, but I wouldn't be able to now.
200s?
Yeah,
You know
that's...
Miss Douglas used to live 200?
Miss Douglas?
Yeah, apparently she was like...
Wow. All right. Okay, now, let me have your attention on this one. We have one more law of thermodynamics. I'm sorry to tell you that our laws of thermodynamics are going to now conclude. We have one more, the third law of thermodynamics. I want you to imagine, you cannot actually have this in reality because if you have something in absolute zero, physically it behaves differently. It starts to get really weird and it loses its volume. But we just imagine. Imagine you have a polar solid. Now, we haven't talked about what polar is, but I think you probably remember from Chem 1. Polar means you have a molecule that's got a positive side and a negative side. Yes? Like the water molecule is polar. One side's positive, one side's negative. It's got to be polar, and I'll tell you why when I show you the picture of it. It's got to be at absolute zero. If you do have a polar solid at absolute zero, it's going to make this arrangement where the positive side of one molecule will be attracted to the negative side of other molecules, and the negatives will be surrounded by positives, and so on. The particles will arrange themselves in a perfect crystal. This is the only possibility for a perfect crystal is if there's no motion of particles. That's why it's got to be at absolute zero. And it's fictitious. This arrangement describes or would define zero entropy. This is the only way we can have zero entropy is if we have this set of conditions. As soon as we raise the temperature, even a little tiny bit, like a half of a Kelvin, the particles will start moving, and they wouldn't be in that perfect crystal arrangement at all moments. So yeah, this is called the third law of thermodynamics. It kind of gives a baseline for measuring entropy.
That's the
So
entropy
absolute
of the
zero.
solid is zero.
Entropy of the solid is zero.
Yes.
So
Right,
that's
right,
the third
yeah,
law.
yeah. The entropy would be 0 only for a perfect crystal where there's no particle motion. So I have two, I guess you would call them ancillary comments with that. First, the more the temperature increases, the more the particles move, and therefore the more entropy they have. The second thing is, bigger and more complex molecules will have higher entropy because they can have more configurations, more movement, or different kinds of movement. I'll show you what I mean by that on the table.
So, but what about, so at the same temperature, would a smaller molecule have higher?
No, a more complex molecule would have a higher entropy.
Even though it's like bigger and it'd be slower?
Yes, even if its particle motion isn't as high, because because the movement is slower. There's more arrangements that it can be in. It can rotate more, and being more complex, it can have different. It can have more possible positions. Which solid do you think on the Earth is the lowest entropy? It's not possible to have it at absolute zero. So at room temperature, what solid is the closest to perfect solid, perfect crystal? No?
Sugar.
Cement.
No, I haven't heard it yet.
Salt. AG.
No. You're familiar with it. You haven't said it yet.
Fluorine.
No?
Hydrogen.
Also not even solid.
Oxygen.
Oh, solid.
Nothing's
Matthew.
a solid.
No, not
Paper.
Tungsten. How are we from
It's not metal.
Boards.
Non-metal.
Non-metal.
Magnesium.
It's got to be a solid. Carbon, be more specific. Diamond.
Diamond.
Diamond is the closest thing to a perfect crystal that we have. Yeah. Now let me show you in the
Play
book.
Minecraft.
Well, yeah, I think you're like, let me show you person.
I don't wear diamond, so I told you I think already why I don't wear diamond.
No, why?
Because I had a diamond wedding ring, but I work on the car and I do stuff, and man, within a few years my diamond was loose.
I'm such a man's man.
Wait, you lost your wedding ring?
I didn't lose it, no, and the diamond didn't fall out, but it was going to. So I said to my wife, I really like my ring, but I can't wear it. So we bought this one. This is who I am. We bought this at Sam's Club for less than $100, and it's been a great ring for me. It's tungsten carbide, which is an extremely hard material.
One of the hardest.
It is.
The hardest.
Yep. And so I never take this thing off, no matter what I'm doing. Working on anything, like when I used to work on the buses, I would just keep my ring on. It's not even scratched. It looks as good as it did the day that it was bought. So yeah, it's a great.
It's probably still be like that for the next 2,000 years.
It's like what?
Sounds like you
Yeah.
Wait, if you wore one on every finger, would it be like brass knuckles?
I don't know what else they use it for. I wouldn't be surprised though. It's really,
Oh no,
really hard.
that sounds dangerous.
So let's take a look at some of our entropy values. Entropy is the last column. You see, it should just say S. It's not actually delta S. But far be it from me to tell the Zoom dolls that they're wrong. And I'm sure they have a reason for calling it delta S. But you can find the absolute entropy of a substance. It shouldn't be delta S, I don't think. Take a look just on this section. What's the highest entropy value? It's the 245 right here. And the 245 would be for bromine as a gas. Of course, gases are going to have the highest entropy. The second highest would be the 199, of course, another gas. And if there are other gases on here, aren't there? Maybe not. If we went down farther, we'd see other gases, but the heavier gases, the bigger ones, do tend to have higher entropy. Take a look at this solid, barium sulfate. It's got a pretty high entropy as solids go. You can compare that to beryllium or beryllium oxide. Beryllium or beryllium oxide has a very low. I mean, look at that. Beryllium oxide is about 1/10 the entropy that barium sulfate is. So, as you see, the bigger, more complex molecules do have the more entropy. So you can kind of get at least a qualitative idea about that. Let's take a look at the diamond. Just to look this down on the page. Can you find it?
Yeah.
Diamond has an entropy of 2. That's the low. I mean, that's pretty close to 0.
What about graphite?
Yeah, graphite is very orderly in range too. And it's funny, diamond is so expensive. Graphite, we buy pencils for like 5 cents when we buy a bulk quantity of them. It's funny that the graphite is almost as cheap as dirt, and diamond is so expensive. It's all about the look of it.
When you get married, you should get a graphite wedding.
All right, we'll see what it says.
Can we just
Okay.
sometimes is valuable?
Now, this guy,
Oh, this too.
but let's not write any of this down. The only thing I want you to write down is this thing right here. This equation is called Gibbs free energy. Yeah, me too. This guy, I don't know if there's anybody, there probably are other people. He actually won 2 Nobel Prizes. This guy was really, really a genius, a thermodynamic genius.
He got one wrong in his reading on this, guys. He's not smart anymore.
So yeah, Willard Gibbs is what they typically called him. His name is Josiah, but they called him Willard. And this equation